Hi, my name is Ethan Bogert, and this is project number 3. So we're going to start by opening Fluent and start with our geometry. So we're designing a simulation for a flat plate for laminar steady state flow using air as our fluid. So from our modeler, set this to Z and get the sketching. So start out with basic rectangle, and then we'll start defining this a bit. So horizontally, I need a definition, and vertically, I need a definition. All right. That is not on the origin. That will mess up my calculations. So we're actually going to go ahead and delete all of this. Go back to sketching, go back to rectangle, and then I'm going to make sure this clips onto the origin like that. There we go. Now we're going to go back to dimensions, horizontal, get these, and my vertical. There we go. And yep, now we're on the origin. Perfect. So I'm just going to zoom in a bit until I get down to 1 meter. All right, so horizontally, we need 100 centimeters or 1 meter. And vertically, I'm just going to do half that. So there we go. There's our geometry. Go to concepts, go from surface sketch, holding control and select all my lines, hit apply, and then generate, and there we go. All right, so that's our geometry done. Now we're going to the longest part, which is our mesh. So we're going to start editing our mesh. Once this loads. It's being a little slow. There we go. Okay. So, starting our mesh, I'm going to do a face mesh, select, apply, and generate. That creates this very basic mesh. Should have. There we go. We'll go back here to sizing real quick and just turn on adaptive sizing. This will be important. In a second. We'll go to mesh, insert, sizing, holding control. I'm going to select my top and bottom, apply, element size, number of divisions, we're just going to do 100. I can actually, I'm going to try to do 1,000 if it lets me. Behavior, hard, no bias, and we're going to generate this. Perfect. Okay. Now we're going to do some more sizing. This time on my inlet. And same thing over here, number of divisions. This doesn't matter nearly as much, so I'm just going to do another 100. Hard. This time we'll have a bias because I want it to be condensed down at the bottom. So factor of 70 should do the trick. Go ahead and generate this. We should see that this becomes very slanted at the bottom here. Yep. That's what we're looking for. Hard to tell here just because there's so much going on, but yeah, you can start seeing it there. The issue right now, we don't have it doing on this side, so let's go ahead and do that. Insert, sizing. I'll select our outlet this time, hit apply. Once again, number of divisions. This is only going up to 100, not 0, 100. Hard, and then yes to a bias. And once again, 70. The only thing we got to do differently here is apply reverse bias. I'm going to select that line. There we go. Now that flips. And generate. Now we should see a very wide mesh. Yep, exactly what we want. Some good meshing up top. But what's most important is down here. Let me drag down. That if I come in here, this is super fine. should give us a nice, good numbers for our plates. All right. Last step before we continue is naming everything. So I'm going to first name this as my flow region. So flow. I'm going to name my far edge. The far edge is the least important part of this. This is our plate. This is our inlet. This is our outlet. Okay. Everything's named. Go over here, hit update. Now that our setup's ready, we'll go ahead and start setting this up. So just throw double precision on, start. Let this launch up. Alright, so just over here in the general, what we're looking for is pressure-based, steady flow, planar with a absolute velocity, and exactly what we want. Our inlet has very dense down here, looser up the top, and the same thing on that side. So we're looking exactly what we want right now, which is perfect. So start over by models. We're going to go from over to laminar flow. Materials, we got to change our air slightly just because of what the project is requesting, that this is 1.2 and this is 1.8. Realistically, this will have a marginal effect, but just for the sakes of this project, we're going to change that. Boundary conditions, inlet, we have initial velocity of 2. Go ahead and apply that. Outlet, it's going to be 0 gauge pressure, so we're going to apply that. Wall, we're just going to verify that these are stationary and non-slip. Yep. Yep. Perfect. Close both those. So we're just going to quickly define that fluid is air. Yep, perfect. Apply. Alrighty, so that's all the setup. Just need to go ahead and initialize now. So just because we know a bit more here, I'm going to compute from my inlet. We're using all this data. That should work fine. And we're going to initialize. We are done initializing. Yep, perfect. And now we're just going to run calculations. Actually, go over to monitors, residuals, and just increase these a smidge. Okay. On calculations, and calculate. That's not what I wanted. 1,000. Should be more than plenty. Okay. Now we can start looking at graphics. So, start with velocity. And we can see that this is the top wall, not really what we care about, but we can see very normal, undisturbed flow with max magnitudes up here. So actually what we're seeing is a maximum velocity of 2.15, which is above our initial velocity. And this is actually what we are looking for, because since down here we have slower velocity, because we're having the boundary layer interrupt this, because the actual outlet is now smaller than the inlet based off of how this velocity is interacting, this almost gets squeezed like a condenser. Or sorry, not condenser, a converging nozzle. So which actually accelerates us slightly. So that 2.15 is what we were expecting. And as we can see, there I can zoom in a bit more. Very thin boundary layer at the top or at the start, and it expands throughout the model. So exactly what we were expecting. Okay, so now we can go ahead and do our pressure contour. Contour. Look at static pressure real quick. Very minor, nothing really much there. Dynamic pressure is going to follow our boundary line. Exactly what we were expecting. And then total pressure. This will look very similar. Yeah, see? Just like that. Cool. Okay. So that's all of the contours. I'm willing to plot my velocity profiles in a second. But while we're over here, I am going to go to results, create surface, and ISO surface. And this is going to be my BLT, my boundary layer thickness. And we're going to do my surface content is my mesh. What am I looking for? Hold on, give me 1 second. Sorry, actually want velocity magnitude. That's what I want. And ISO values, it's 1.98 because that's going to be 99 of my free flow velocity. And then I'm going to hit create. Okay. So now if I plot this, that's my, what do I want to do? This is my mesh. And then I hit save and plot. So yeah, so as we can see, as we move along, that's not what I want to do. I should probably do this as a graphic. No, I'm thinking about it. Contours. Contour of fluxes? No. Mesh. I mean, there we go. That's not exactly what I want, but I can pull my data from there. But you can kind of see the boundary layer line. I do want to graph this somehow. I'm just forgetting how to do that. There we go. So that's showing the boundary layer thickness throughout the entire thing. So at the very edge, that's a very small 0.009 meters thick. So about what we expected, but you can kind of see as it grows, starting at near 0 and then growing all the way up to 0.009. All right. So that's the boundary layer thickness, and I guess I can go ahead and show my velocity profiles. So let's go over here. Go here. I'm just going to create some new lines real quick. So this is L25. And what I need is 0.1 be at 0.250. And then 0.2 to be 0.25, That should be a vertical line. And we'll do 1,000 samples. Apply. Yep, that's exactly what we want to see. Throw symmetry on real quick. Just make this look a little more observant. What do I want to do in our line? This one's going to be L50. Okay. This time, 0.5, 0.5, but this time 0 and 0.5. Play. And one last time. Do this as L75. That's on 5. That's on 5. 0. 0.5. Apply. So we have 3 vertical lines, exactly what we wanted. And now we're going to go up here. And well, hold on. Let me just quickly put that in full screen. XY plot. This is going to be our velocity profiles. All right, so XY, we'll just do velocity profiles. Data series, I need 3 separate series. Series 1 is going to be L25, Series 2 is going to be L50, and Series 3 is going to be L75. Apply. So my x-axis, I want this as velocity u, this as x. Actually, no. I think I did want this, and then this as y. Yeah, there we go. So what we're looking at is Series 1 having this kick out here as we approach the edge of our boundary line, which is what we expect, a little bit higher speed. Curls back in and goes vertical. We're not seeing that here because I believe I forgot to... Yeah, these are only at 10 samples, so that's why. So we'll see something similar once... Yeah, there we go. Okay. Apply. There we go. Now we're seeing more what we should be seeing, which is this very similar profile because our actual boundary layer is not very thick. So, but as we expected, as we further along, this line grows taller. But we have that curve at the end where it pinches, and the air speeds up and it slows down and it gets constant all the way up until we reach that top line. So in real etch applicable, this wouldn't really exist here. This would not go back to 0. But just how we are running the simulation, this line is being applicable. I'll do the table in the project report. I just don't have that filled out right now. So now we're going to go back to our basic Fluent, and we're going to start looking at shear stress and skin friction coefficient. Actually, I lied. I do want to be in this. So, same thing. Do this one as skin friction. Okay, so this one we're going to need 2 series. Series 1. We'll go back to Fluent. We're going to go to wall fluxes, wall shear stress. Actually, no, I want skin friction coefficient. Position on the x-axis. And I want this as our whole region. It's on the plate. So that's our skin friction coefficient along the plate. Okay, I will have to convert that before showing that, but I can. Hold on. Okay. And then Fluent, I can actually write the file. Right. And I am going to actual. Okay, so now I can actually probably do file and same thing here. Open this and apply. Cool. That's only going to accept CSVs. So I guess I can show these both real quick. On the same section real quick. Okay. Nope, that's not one. This. Okay. So on the left we've got our theory, which okay, I'll fix that later. It's fine. That's saying wrong, but here we go. And then we'll go ahead and show wall shear stress as well. So there we go. That's my wall shear stress. To get my drag coefficient, I'm going to come down to, where is it? Surfaces? Nope. That's not what I want. For definition? No. Force support, drag. Drag coefficient. Compute. Far edge. No, plate. Compute. There we go. CD is 0.016430086. All right. So that's everything you asked for. I will prove theory and actual in my report once I figure out how to convert everything.